Welcome back to the Structured Cabling lecture series. This is lesson number 7 and I'm going to go over signaling basics. If you haven't seen my previous lectures, I will post a link in the description for the playlist. Please recall from my previous lectures that copper cables use electrical pulses or energy to transmit data, while the fiber optic cables use light pulses or photons to transmit data. We can send both analog and digital signals using either medium, whether copper or fiber optic cables, but typically fiber optic communication cables are used for digital communication when we use them in infrastructures, etc., etc. Typically, the network systems, also known as NAS, use packet switch data, and the data is almost always going to be digital in our network engineering systems. In this lecture, I'm going to cover a little bit of theory related to signaling. So signaling is a little bit of more complicated area in this particular subject matter. However, if you are a technical student, if you are a student in a technical school in North America, you just need to know the basics of signaling. You don't need to know the mathematical formulas and configurations and how we manipulate the physics and math side of signaling. So I'm not going to introduce you to any math or physics concepts that are very, very advanced or even intermediary advanced concepts, just to keep this lecture as light as possible. However, as a result, you may find some of the concepts that we're going to cover today is a little bit choppy. In other words, like I will be pulling information here and there without going into detail. But at the same time, I will explain enough information for you to understand the fundamental concepts of signaling associated with how cable infrastructures work. So, first thing first, we need to know what is a signal. Signal is a way of communicating by sending information from one system to another system. In other words, signal allow us to communicate information that are generated from one system to the other system. So we have an exit or output signal that been sent out by the one communication system, and the input of the next system going to use that signal data to process that information. So in other words, signal is a function that represents some type of information or data. Signal is a function of one or more independent variables in which contain some information. So the signal, if somebody asks you on an exam or somebody in the field asks you what is a signal, you can give the definition. Signal is a way of communicating by sending information from one system to another. And if you want to give a little bit of more detail, you can say signal is a function of one or more independent variables which contain some key data or information. What is information? What is data? I have already covered in my previous lectures on my YouTube channel. Basically, what separates information from data is data could be like just a value. Information is there is more information, more details associated with that particular data value. For example, if I tell you temperature is 20 degrees Celsius, that could be considered as a data. But if I tell you the temperature in Calgary, Alberta, Canada on the October 11th morning is 20 degrees Celsius, that 20 degrees Celsius data become information. So data is just a value. Information is something that contains some additional pieces that makes that data into an information. So that's what you need to roughly understand, the difference between information and data. That's not very important to this lecture. It's just, I just want to throw it out, because if somebody looking at this slide and goes like, well, what's the difference between information and data? And that's the difference. In computing, we can use voltage and current to generate signal. So for example, a digital signal plus or minus is sometimes used for the digital signals up and down, or plus or zero. For example, plus 5 voltage can be considered as a 1. Anything below plus 5 voltage can be considered as 0. So between 0 volts to 5 volts, it's going to be considered as 0. But as soon as the signal goes above that plus 5 threshold, for example, we consider as 1. Because remember, in computing, we are using zeros and 1. which I will cover in the next few slides as well. But a signal can be represented of physical energy using mathematical function. So for example, temperature, as I mentioned, the pressure, etc., etc. So the signal can be represented any type of physical energy, not just computer data. So keep that in mind as we move forward. What is a system? So in my previous slide, I mentioned something about input and output of signals from one system to another. Now, what is a system? So we need to have a definition of a system. A system is formally defined as an entity that manipulates one or more signals to accomplish a function. So this function will result in a new set of signals as a result of processing. So in other words, a system process signals or system process data that being carried into the system by the signals. So system will take a signal either from another system or some kind of a generating mechanism and take that signal and process and generate new form of signals. That's what make a system a system. So in our communication systems, as well as our digital and analog system, we use this kind of devices such as computers, servers, switches, routers that use these signals and do something with it before sending it out. So if somebody asks you what is a system is defined as an entity that manipulates one or more signals to accomplish a function. And when this function is accomplished, the input signal going to be different from that of the output signal, because the system will be processing the input signal to produce that output signal. So the next thing we need to think about is analog communication systems are identical to that of the digital communication systems, because we have two forms of major division in systems, one called the analog communication systems and the other one called the digital communication systems. So in simplest term, they are similar in terms of how the systems operate. It takes a signal, process it and generate another signal. However, they are fundamentally different on how those systems operate. So the analog communication systems operate differently that are compared to the digital communication systems. And the next few slides, I'm going to describe those things as well. Analog and digital systems. So the analog communication system composed of a modulator, channel, and a demodulator. What are modulators? What is a channel? What is a demodulator? Not that important for you as a cable technician, but you need to understand an analog communication does have a modulator, channel, and demodulator. I'm going to describe to you how the modulations and demodulation happen in the next few slides in a very high level brief overview without giving you any mathematical formulas or anything like that. But what you need to understand is that analog communication contains different components such as the modulator, channel, and demodulator. Digital communication systems contain sampling, quantization, quantization is the way of like quantifying something, coding, and then we have the transmitter, channel, and receiver. So we have the sampling, quantization, and coding in the one side, and then it's gonna put it into a transmitter, channel, and a receiver. So notice that some of the components are similar, such as the channel. Right here we have a channel, we have a channel here, but there are some additional components associated with digital communication systems. For you, you just need to understand that the analog communication systems are less complicated compared to digital communication system, but we still use the digital communication systems nowadays more than analog system, because digital communication systems allow us to do more things and have more capabilities compared to analog communication systems, even though digital communication systems are a little bit more complicated compared to the analog ones. So they are similar, but they are not identical. So they are even different at the most fundamental level of operation. So the fundamentally how they operate different from each other. However, they are very similar to each other. What is modulation? So I'm introduced to you something called modulation and demodulation. So I'm gonna now give you a little bit of an in-depth analysis of modulation without giving you any mathematical formulas, physics formulas, or math formulas. So it's easy for you to understand the fundamental concepts at a very high level. Modulation is a process in which some characteristic of a signal called the carrier signal is varied in accordance with the with E value of the message signal. So that's the definition of what a modulation is. What is a E value? What is a carrier signal? Well, you don't need to know that, so I'm not going to cover those in depth, but you need to know modulation is a process in which some characteristics of a signal called carrier signal is varies. But you need to know why we do this change. Why do we even modulate the carrier signal? To understand that, you also need to understand what we have other than the carrier signal. So other than the carrier signal, we have the message signal, which is also known as the modulating of baseline signal. So two components, we have carrier signal, we have a message signal. In modulation, what we are doing is we are varying the elements associated with, in other words, characteristic of the carrier signal itself, not the message signal. So to give you a high level overview, carrier signal is basically what carries the data. Message signal is what the actual data is. So that's why we don't change the message signal itself, but we actually change a lot to do with the carrier signal. So resultant signal after modulation is known as the modulated or bandpass signal. So the message signal is known as the modulating of band signal, and the carrier signal is varies in accordance with the E value of the message signal, and then resultant signal after modulation is known as the modulated or bandpass signal. Again, you just need to know how basic signaling works. You don't need to know in depth. I will maybe post a different separate lecture on high level to most intimate level of analysis of how modulation works in the future. But for now, for this particular lecture series on structured cabling, you just need to know what modulation is about and how it works. So this slide basically describes what all you need to know at this moment. So when it comes to the point modulation, there are different types of modulation. I mentioned before, there are major division in modulation, one called the analog and the digital. So we have a analog carrier modulation and the digital carrier modulation. Analog carriers, we have the analog data and digital data divided, and then we have digital carrier, we have analog data and digital data broken in here. So I'm going to go over some of these items because things like PCM, which is a pulse code modulation, is very important to cabling. So if you are using things like fiber optic cables or any kind of data communication transmission cables, even telecommunication cables, they all use PCM at some point. So because of that, I'm going to go over some of these things, but I'm not going to go into in depth. So keep that in mind. So if you want to know the overall view of the modulation, you should pause this slide. In fact, you should actually copy this slide. If you have exams, you should memorize maybe these different divisions, because there are logical reasons why we have these divisions. You should understand the in-depth of these things if you are in the engineering side of the equation. But currently I'm trying to educate general public as well as the technical students in technical schools in North America how modulations work. So for that, you don't need to know in depth of this other than the modulation have these divisions. So let's look at the reasons to modulate. To work within the limits of antennas and transmission devices is the primary reason why we modulate, because we have transmission devices such as fiber optic cables where we use in structured cabling that may not support all the wavelengths and all the digital frequencies that we can send. So that's why we modulate, so that we can work within those antennas and transmission devices. So the analog wavelength supported by transmission mediums, for example, varies between different antennas and devices. Therefore, we use the modulation to make sure that those antennas can support the data which we try to transmit. We also use modulation to remove interferences. So if you have noise or other interferences in your signal, we can use modulation to remove those interferences. Remember, modulation involves a lot of mathematical equations and signal processing mathematics, as well as some statistical equations. Those can actually remove certain interference from a signal. Not to go into details on types of modulation with respect to analog signals, but we will discuss the digital side of a little bit more detail than the analog side of things, because we are interested in computer engineering and network engineering side of modulations in the next few slides. Next, we're going to discuss the digital modulation. Analog signal can carry digital data. This is a very important concept that a lot of people don't understand. You can have an analog signal that contain digital data. Digital to analog to digital conversions are where the digital modulation come into play, because they are actually converting between the digital signal and analog signal and digital signal. Because analog signal can carry digital data, we can have certain parts of the system that is on analog and the other parts in digital with these type of modulations. Amplitude shift keying is one of the ways that you can modulate a digital signal. Again, you don't need to go into depth of these things if you are a technical IT student in a technical school in North America, but I'm going to give you an overview of this. I basically straight pulled these things out of the internet. I didn't write these things. These are already written by engineers and scientists. I'm just going to give you the overview. So I'm going to go over a few digital modulation concepts. But again, this is very important. We are just covering the surface. So amplitude shift keying, basically the amplitude of an analog carrier signal varies in accordance with the digital modulating signal, keeping frequency and pace constant. The level of amplitude can be used to represent binary logic such as zeros and ones, and we think of a carrier signal as on or off. So when you have a 0, we are on, off, and when you have a 1, we have a on. So 1 is on or 0 is off. So because digital can only represent zeros and ones, the level of amplitude on the analog signal can be used to convert into binary logic zeros and ones when we are modulating from analog to the digital. In the modulator signal, the logic 0 is represented by the absence of a carrier, and logic 1 is represented by the presence of a carrier. Here the carrier means the carrier signal, thus giving off and on keying operations, and hence the name is given, because we are doing amplitude shift keying. We are keying the analog signal into digital zeros and ones. The ASK technique is also commonly used to transmit digital data over fiber optic communication systems, also known as fiber cable. So this amplitude shift keying is very important if you are working with fiber optic communication lines, so optical fiber optic lines, as a cable installer and become a cable engineer. So this ASK, amplitude shift keying, is important to not only telecommunication industry, but also for IT and computer network systems engineering industry as well. The next one I'm going to briefly introduce you is the on-off keying, also known as OOK. Again, a high-level overview of this is basically it is a modulating scheme that consists of keying a sinusoidal carrier signal with the on-off with unipolar binary signal. So basically it is a simpler form. What you need to understand, it is the simplest form of amplitude shift keying. So the on-off keying, OOK, is a type of amplitude shift keying modulation that represent digital data as presence or absence of a carrier wave. So that's basically what on-off keying does. I'm not going to go into any more detail. If you are interested in how on-off keying working, please Google search it. If you are in the engineering side of this type of structured cabling subject matter, for now that's not my focus. So I'm just going to move on to the next one. It's called the phase shift keying, PSK. Phase shift keying is a digital modulation scheme that conveys data by changing or modulating the pace of reference signal or the carrier wave. Remember the carrier wave I introduced a few slides back? So that's what we are discussing here. So the PSK uses the finite number of paces, each assign a unique pattern of binary digits. Two common examples of phase shift keying includes the binary shift keying, which uses two different phases, while the quadrature phase shifting keying uses 4 different phases. Quadra mean 4 and the binary is 2. So that's all you need to remember with the PSK. With going back to the on-off keying or OK, I just want to point out the OK look like this. So you have an analog signal and there's no signal. Then you have analog signal and you have no signal. You have analog signal, you have no signal. And whenever there is this analog signal, we can create a 1 in the digital signal. And when there is no analog signal coming through, we can actually put it as a 0. And then the digital signal look like this, which is very similar to what the analog signal burst that go with the on-off keying. OK, so this diagram is associated with OK up here. Again, this is a high level of overview, so you understand the basic fundamental concepts associated with signaling when you are doing structured cabling in network engineering and network systems. The next one is called frequency shift keying. Frequency shift modulation scheme in which digital information is transmitted to discrete frequency changes of a carrier signal. So that's why the frequency shift keying is about. So the frequency shift keying can be described as a frequency modulation scheme in which the digital information is transmitted through discrete frequency changes of a carrier signal. So you have the data that have a digital signal like this, and if you look at the carrier signal, it'll look like this, and the modulating signal look like this, where the modulating signal and the carrier signal become dense like this, as you can see, and they actually have a specific mathematical agreement. Then the digital signal going to have a 1 here. When there is no density in the modulating signal and there is no mathematical agreement, then you're going to have a 0 like this. So that's why the frequency shift keying. Again, this is a very high level overview. Again, I may do a different lecture on the more detailed overview later sometime. I'm going to introduce you to something called the quadrature amplitude modulation, or QAM. QAM is both analog and digital modulation scheme. This is very important in certain applications, such as sometimes VoIP application, because human voice is more analog as opposed to digital. So the QAM is both an analog and a digital modulation scheme. So it conveys 2 analog message signals or 2 digital bit streams by changing the amplitudes of 2 carrier waves using the amplitude shift keying. Remember the ASK I introduced and the digital modulation scheme. So what you need to know in here, there's a lot of text in here. What you need to know is a QAM is typically used in, like, things like VoIP communication sometimes, because it is using the amplitude shift keying digital modulation scheme or amplitude modulation, AM analog modulation scheme. So you can use either or to do the modulation. These 2 waves usually sinusoidal and are out of phase with each other by 90 degrees and are thus called the quadrature carrier or quadrature components, hence the name of the scheme. The modulated waves are summed and the resulting waveform is a combination of both phase shift keying, also known as PSK, and amplitude shift keying, also known as ASK, or in the analog case of modulation, it's just going to be PM or amplitude modulation. The digital QAM case, a finite number of at least 2 phases are there and at least 2 amplitudes are used in this QAM scheme. QAM is used extensively as a modulation scheme for digital telecommunication systems. That's why I said the VoIP communication, for example, use QAM, and as a cable installer or a cable technicians, it is better that you understand that the QAM exists so that you have a better comprehensive overall view of what you are installing and what you are dealing with as a cable installer. So again, the QAM is used extensively as a modulation scheme for digital communication systems, such as the VoIP systems, where we use this kind of QAM on those Cisco phones, for example. Sampling. Sampling is a very important concept, even though there's not much data on this slide. It is basically a mechanism of converting continuous signal to a discrete time signal. So if you have a continuous wave and you need to get information from that into digital format, what do you do? Actually sampling. When you pick up a VoIP phone and start speaking to someone, basically that person hear the digital sampling of your voice, not the actual analog signal, because human talk in an analog form. So sampling allow us to get as close to the natural voice, but not the natural voice itself. This is why when you are communicating on a cell phone, for example, or when you are communicating on a, let's say a Microsoft Teams discussion, your voice will be slightly different from when you are speaking to someone face to face. So the voice is going to be different heard by other party. The reason for that is the other party actually hear your voice in a sampling technique. Even right now when I'm speaking to you, I'm using a digital recorder on my Windows 10 machine to record this lecture. This lecture's voice is recorded using a sampling technique, because my computer is digital, but my voice is natural analog signals, right? Because in nature, everything is like a sinusoidal curve. So whenever you speak to someone, doesn't matter what language you speak, whether it's English, French, Sinhalese, or some other languages, you always speak in that type of a sinusoidal wave format. So sampling allows us to convert that, wave format into a digital medium. So what I'm saying is, when you speak, so if you're speaking, your speaking volume and the voice is going to go like this. But the sampling, what that's going to do is basically it's going to sample this wave here and there, and then going to get those samples put together into some kind of a digital format like this. My digital signal is so bad. So to allow that to be communicated across network systems. So that's what you need to understand in this particular slide. So the sampling theorem says a continuous time signal may be completely represented in its samples and recovered back if the sampling frequency is fs, blah blah blah, and where it is fs is a sampling frequency and the fm is the maximum frequency of the represented signal, right? But the thing is, like, you don't need to know what is fs greater than or equal to 2 fm means. You don't need to know any of that. What you need to understand is, when you have a VoIP phone on your network, for example, the signal looks like this, as I mentioned, but actual signal that the VoIP phone going to communicate through your fiber optic system is going to look like that, or something like that, and then it's going to convert back into the sinusoidal curve that heard by the other party. Typically that's what happens. Sometimes they just hear this part, but what you need to know is a sampling is very important, especially in VoIP communication systems when you are dealing with network engineering and computer science. Next one, we're going to cover also an important concept called the pulse modulation. In this case, the carrier wave is no longer a continuous signal, but consists of pulse train where the pulses are used to communicate data. So instead of having a continuous sinusoidal curve, you're going to have a pulses or burst of data coming through the system. And I'm going to introduce you a little bit of more concept associated with pulse modulation. The pulse modulation is used especially in VoIP communication system, but also in data communication systems for high-speed internet and etc. as well. So the pulse modulation has pulse amplitude modulation, pulse width modulation, and pulse position modulation. What you need to understand for now is that pulse amplitude modulation, also known as PAM, is basically amplitude of the carrier pulse train is varied in accordance to the modulating signal, and the pulse, that's what make it a pulse modulation. And then the next one we're going to look at is the pulse width modulation. So the pulse width modulation is the PWM, in which the width of the pulses is proportional to the amplitude of modulating signal. So this is looking at the amplitude, and then this one is also looking at the amplitude, but PWM is the width of the pulse is proportional to the amplitude of the modulating signal. And the PAM is amplitude of the carrier train is varied in accordance with the modulating signal. And the next one we're going to look at is the pulse positioning modulation. That would be this one. And in PPM, the position of the pulse with reference to the position of the reference pulse is changed accordance according to the value of the modulating signal. If you don't know what amplitude and width and stuff like that, I should have introduced those to you in the earlier actually. So if you have a signal, an analog signal like this, right, and if you have a center line like that, so this is what we call the amplitude pretty much. So those are like how high this thing goes, and then frequencies like that would be considered as frequency. So like things like that. So these concepts I assume you already know from high school, but amplitude is like how high the thing is, the wave is, the frequency is how often this thing gonna get repeated. So that's what you need to, like, that's the background you should have by now. So keep that in mind. This is a very important concept called pulse code modulation, or PCM. This is something my dad is very familiar with. My dad used to work as an engineering technician and an engineering specialist for Sri Lanka Telecom long time ago. So the pulse code modulation is something that my dad did with his fiber optic cabling work. So the pulse code modulation, or PCM, is a digital pulse modulation system, and the output of the PCM is in the coded digital pulses of constant amplitude, width, and position. And then the basic operations on PCM are basically sampling, quantization, encoding. So basically we have a sampling which goes into quantization, which then converted into encoding. Remember, I have introduced these things in the very beginning of this lecture. So this is where they become also very important. So sampling is basically, recall from my previous slide, basically taking a sample of the signal, such as I told you, like when you're talking to someone, it's a analog curve. To convert it into digital, we take samples. So that's what the sampling is about. Then the quantization is basically the process of dividing the total amplitude range into number of standard levels. And what are standard level, how we divide it is more mathematical and physics, which again I will introduce you to maybe separately on a different lecture that goes into math side of things. But you just need to know that the quantization exists and what basically it does. And then the encoding converts the quantized input signal into binary words. You probably have heard the term encoding before when you are dealing with digital media, such as voice media or videos, audio, video files, when you are working with Windows and Mac computers. This is what basically they do too. They convert the quantized input signal into binary words so that the binary can be understood by your computer. So at the end of the day, what the PCM is doing is taking the sampling, take that into quantization, and then convert it into going into encoding. Next, we're going to cover something called analog signal, which is an important signal. As I mentioned before multiple times, analog signals are sine wave or sinusoidal waves, and they look like this. And then the sine wave look like this and a cos wave look like this, but it's very, it's a variation of the sine or cos wave is what we get with the analog signal, because variations can be, as I mentioned before, you could have a signal doing something like, let's say like this, like that. It's a really poorly drawn one, or you could have a signal that very close to that of a sine wave like that. So you could have a signal that started out with very close, then it goes like this and then goes everywhere. So it's, at the end of the day, it's a manipulation of a sine wave or a cos wave. And basically these type of waves are what we call the natural wave compared to a digital wave. Everything in nature seems to have these type of waves, whether it's the temperature changes, how the earth rotates, have a similar waveform like this, how we speak, our voice go wave like this. So analog waves are natural as opposed to digital waves, because digital waves are blocky, right? Remember, digital waves are very blocky waves, and then in those blocky digital waves have things like this, right? So that's what the digital blocky waves look like. So these are not natural. So have this wave format is more natural than a digital wave format like this. Imagine this is like blocky like this. I'm a very poor drawer here. So keep that in mind. So that's very important concept that everybody should understand. When we speak, or whenever we detecting natural things such as temperature changes on your sensors at the end of your network, that network, the sensor is actually doing natural waves. But when it get transmitted, we convert that into maybe the digital format. So because we are dealing with a lot of natural things such as voice or natural data, natural frequencies, we need to convert analog into digital format for communication. So we do convert analog signals to digital a lot in almost every industry. The best example for our industry, cabling and communication industry and computer system industry, is the VoIP, because VoIP is an example of a sine wave signal converted into a digital for transmission and processing. So whether you are using Microsoft Teams, whether you are using some other format such as Discord or something like that to communicate, we basically take the sinusoidal curve like this and convert that into digital pieces by sampling, and then we send those samplings through the communication medium, and then we can convert back into either the analog signal or to just give the digital out. That's why your voice sounds slightly different when you are speaking on these kind of mediums such as MS Teams, as opposed to when you speak into someone directly. Your co-workers and your friends on the other side, you may hear slightly different. Some people actually can pick those differences, but most of us we don't hear it because it's pretty close, right? Because if this is somebody's voice up here, and you can see it's pretty close to what the other guy is doing. So this green part right down here is a representation of the blue part up here, right? So because of that, right, this blue part and this blue signal could be your voice, that your direct voice signal, and then this green part basically can be considered as your other the converted signal, right? So when you're communicating through a digital medium, what I want you to understand is that you don't get this exact natural curve on the other end, but very, very close to that natural curve, so your friends can understand it's you who is speaking to. So, however, like I said, when you meet someone face to face, you'll notice sometimes their voice is slightly different from that of what you hear from things like MS Teams. Analog signal conversion to digital is not perfect, therefore, because we are using sampling techniques. So in VoIP communication, as I mentioned multiple times, you don't actually hear the natural voice of the other person. You hear the digitally converted voice of the other person. Modern conversion algorithms, however, try to achieve a digital signal that is as close to as natural human voice as possible. As a result, some of us can't actually tell the difference between a digitally heard voice versus an analog natural voice. Medical devices that monitor human health factors such as heart rate therefore still use analog signals as a result, because we don't want to be in a situation we have medical devices that are actually monitoring things like heart rate. That's going to be actually a natural signal, which is mostly analog, or it's pretty much analog, to have some kind of a variations or differences causing medical doctors to misdiagnose especially heart conditions and etc. So if this is the situation, if analog signals are so much everywhere, and it is in nature, it is in human health, it is in temperature changes, it is in how the earth rotates and etc., why do we even bother to use digital signals at the first place? Well, there's a reason why we still use digital signals, because digital signals are faster for data communication over long distances. And there is no disadvantage when it comes to just data communication. So if you're sending a web page to someone, using an analog signal going to be pain, and it's going to take more resources, probably going to take more time to send that information. It will take more time to send that information. Digital, because we are using zeros and one, it is much more faster, and for what the purpose of data communication, what it is used for, there is actually no disadvantage at all for using digital communication. Even voice communication, as long as you understand what I'm talking to you, what I'm trying to describe, and if you understand my words, if you can describe the same thing that I'm describing to you by listening to me, well, that means our digital conversion, digital analog modulation works fine. So right now, the voice that you are hearing through YouTube channel on my NetIT Geeks is basically my analog voice converted to modulated to digital, and that's what you're actually hearing. You are not hearing my natural voice. You are hearing a digitally converted voice. But there is not really disadvantage to that either, actually. And advanced digital communication features associated with digital signals such as conference calling and integrated packet switching security that associated these type of digital signaling are much more versatile and important to us today than to just go with analog signals. And also a digital signal allow us a flexible deployment and maintenance and troubleshooting options as well. A VoIP communication system is easy to deploy, easy to manage, easy to scale. So if a company start with 100 individuals and decided to go to 300 individuals in the next few months, it's very easy to scale it up really fast because for example, Cisco VoIP communication systems, you can basically install on any server and you just increase the server hardware capabilities. Maybe even that may not be needed, and you can simply deploy a VoIP system in a fraction of a second. There are many other VoIP applications you can do that, and therefore it's the flexibility in deployment, maintenance, and troubleshooting is also easier with the digital system, as opposed to if you have an analog PBX or PABX system where you have a switching equipment for your internal telecommunication systems on a building. Whenever you go from 100 employees to 200 or 150 employees, you may have to do more hardware upgrade in order to do that, as opposed to a VoIP system. So that's why we still use digital. It is faster for communication in long distances. No disadvantage when it comes to data communication, such as sending a website, etc., and advanced communication features associated with that, such as conference calling, security, etc. And also it includes some very good flexibility and maintenance and troubleshooting options. So that's why we still use digital, even though analog is what we naturally see in nature. So here's a brief few slides on digital signals. So digital signals, as I mentioned before, only deal with binary values. So it's either 0 or 1. So here's a digital signal we have on the right hand side of the screen. We have a 0 or 1. That's all digital signal can represent. And signal is transmitted as a square wave as a result. So we have a positive voltage and voltage over time represented. So we have a positive and a kind of a negative voltage or a 0 voltage that represent ones and zeros. So this could be a 0 voltage or a negative voltage that represents 0, and you have a threshold for that, and then you have a threshold for a positive voltage that will represent 1. For example, if you have an digital signal, and if a digital signal is over 5 volts, for example, we can consider that as a 1. If the digital signal is remain below 5 volts, so between 0 volts and 5 volts, for example, we can consider that as a 0. As again, if you go into over 5 volts, we can consider that as a 1. So that's an example of having a threshold. So that's what I'm describing here. So to eliminate incorrect wave formats, signal must be above a designated threshold voltage to represent a positive voltage, which is 1, while the signal has also to be below a designated threshold voltage to represent a negative voltage, which is a 0. So if the voltage is between 0 and 5, it will be considered as 0. But if it is just above 5, it's going to consider as 1. And again, drop below 5 volts, it's going to be 0 again. So anything below 5 volts, I can say it's a 0 value. Anything above 5 volts, it can be 1 value. So it could be 5 volts, 6 volts, 7 volts, 10 volts. It's still going to be representing 1. But if it is below that 5 volt threshold frequency, we're going to represent a 0 at a certain level. So it's not just anything below. I kind of misworded that. So we're going to say like 0 volts, anything below 0 volts or negative value is 0. Anything above 5 volts is a 1. So if a signal drop below 5 volts, it's not a 1, but it's still maybe as 1 until you hit that threshold for the 0 value. So that's why even the 0 value has to be have a designated voltage, so that you will eliminate incorrect wave formats, noise, etc. Signal timing is also important, as it is not within a designated threshold of time, it will not be recognized. So time domain in here is represented on the left to right. So this is the time of which the signal is being produced, and this is signaling going up and down within that time. So this could be a 1 second or 5 second or whatever, and that can be designated, and those designated time value will be then used for communicating that information. So basically signal is over time. So we're getting zeros and one over time. So here's an example of such thing. So I'm going to say a 0 has to go below this line, and then 1 has to be above that line, but not just because of signal is right here. So if you have a signal, let's say right here, if the signal goes like this, that's not a 1. 1 has to be above a certain level, and this is not a 0 either. It has to go below this line and also has to be below in a certain level. So what that means is basically we have an unknown zone. So the zone between this line, so zone between here and zone between here is what we consider as an unknown zone. So in this unknown zone, basically we don't take any measurements. So when you have a digital signal, when you have try to convert this analog signal into a digital format, even let's consider this as an analog signal, for example. This signal right here, all 1. So it's a one single 1 because this hasn't dropped below that unknown zone. But as soon as it drops a little bit below unknown zone, let's say its unknown zone is right here. Like if the unknown zone start right here, this is going to be 1 and this is going to be nothing and this is going to be 1 again, because that's the threshold we can. But because we define this is as the unknown zone right in this yellow bits, this is basically the unknown zone. So what happened is as long as you are in between here, it's not going to be nothing, but anything below this box gonna be 0. So this is going to be a 0 right here represented. Anything above this zone going to be 1. So we have 1 0 1 1 because this is remaining in 1. So even though it didn't drop, so that means this is going to be a digital curve going to be like whoop, like that, and here the digital curve going to be like that. So this is a shorter digital one, this is a longer digital one, and we're going to have a digital 0 represented right here. But anything in between is nothing in there. So this signal could be like this. So we're going to have like that, and then I'm going to have a longer one like that. So this is what this signal is about. So in between we have that unknown zone where we have set those thresholds that I described in my previous slide to define that digital signal. You need this definition to eliminate any unwanted signal and noise. At the end of the day, what you need to understand for this lecture series is the differences between analog versus digital signal at a very high level. And this slide basically summarizes all of that in a one go. You can post this slide, you can print this slide, you can use this slide for studying for your exams and quizzes if you are in a technical school and not in the engineering side of things, because we are not covering the engineering side of mathematical formulas, even though I introduced you to a lot of technical concepts in this lecture. So what you need to understand for this lecture series is that analog signals is continuous and vary with time. Digital signals have 2 or more states in binary form. So they are either ones or zeros when it's come to the point, the digital signals. Analog signals, troubleshooting of analog signals are difficult because they are like sinusoidal curve, sinusoidal waves, and they may have some noise associated with that. They are a little bit harder to eliminate or separate, filter out as opposed to a digital signal. Digital signal, therefore, troubleshooting of digital signals as a result are much easier because they just have zeros and ones. An analog signal is usually in the form of a sine wave, as I mentioned multiple times, while the digital signal is usually on a square wave. Analog signals are easily affected by noise because everything in nature has an analog signal. So microwave towers get oftentimes impacted by solar waves and a whole bunch of other things. Sometimes, like not necessarily solar waves. Solar waves actually impact like FM, AM transmission sometimes, because those are all natural things, have analog waves. So analog waves can interact easily with other analog waves that we use for transmission purposes. Digital waves are more stable and less prone to noise, but it still can be affected by noise. So it is less prone, but it still can be affected by noise. Analog signals use continuous values to represent data. So there's always some kind of a value representing data with analog signal, while the digital signals use discrete values to represent data, which are zeros and ones. Accuracy of analog signals may be affected by noise. However, the accuracy of digital signals are typically immune to noise, but sometimes, it can have an impact as well. Again, digital is way immune to noise compared to analog signals. However, it still can be affected a little bit. Analog signals may be affected during data transmission, while the digital signals are not affected during data transmission in most cases. Analog signals use more power, digital signals use less power. So during transmission, you can use less power to transmit that information. Whether it's electrical power or photons, at the end of the day, analog signals require more power. Examples of analog signals include temperature, pressure, flow measurements, etc. Examples of digital signals include valve feedback, motor starts, trips, etc. But you can convert between these two using what? Modulation. You can use modulation between the analog and digital and convert these two back and forth. Components like resistors, capacitors, inductors, diodes use analog circuits, while the components like transistors, logic gates, microcontrollers, which we use a lot in computer science and network engineering, use digital signal. Again, this lecture is very theory heavy and cover areas that you probably never need to use in the real world technical field. But however, understanding these fundamental concept is very important as a cable installer or a structured cabling specialist, so that you have a background knowledge, so that will enhance your understanding of cable installation process and network engineering. And that would bring us to the end of this lecture. If you have any comments or concerns, please make sure to reach out to me. If you like these type of videos, please thumbs up this video and subscribe to my channel. Until next time, thank you so much and have a nice day.